This episode is brought to you by Cisco Educational Premium. For ages, it has been said that mathematics is the mother of all sciences. All the concepts of science stem from mathematics. This alma mater, the nourishing mother, mathematics is truly astounding. And what better concept to demonstrate this than the birth of light as a consequence of solving Maxwell's equations? Maxwell's equations are 4 in number. The first is the Gauss law for electricity, which relates the net electric flux to the net enclosed charge. The second is the Gauss law for magnetism, which relates net magnetic flux to the net enclosed charge. The third is the Faraday's law, which relates induced electric field to the changing magnetic flux. And the last but not the least is the Ampere-Maxwell law, which relates induced magnetic field to the changing electric flux and to the current. But wait, Caleb. What they call Maxwell's equation again? That's a story for another day. Now, the real deal. This is a math show. We're not going to just make sense of statements, but crucially piece together reality from numbers, from mathematics. No shortcuts. These are Maxwell's equations in their differential form. In a vacuum, when there are no electric charges and currents, our Maxwell's equations will evolve to as shown. Our equations are now simpler. The first and the second equations are the divergence of electric and magnetic fields. These two are telling us that if there are no charges present to create magnetic and electric field lines or terminate them, there will be no divergence. The fields will be continuous. They will not start or end. Astonishingly, Maxwell's equations, even in completely empty space, can define and allow the existence of magnetic and electric fields. The other two equations deals with how these continuous electric and magnetic fields behave. The third tells us that the electric field can be created by firings of magnetic fields in the vicinity. Same as the third, the fourth equation tells us that we can get some magnetic fields in the vicinity by firings of magnetic fields. Both of these fields must be at right angles to one another for one of these fields to generate the other. Say in the third equation as shown. Remember mathematically, the left hand side of this equation, del cross E, we are taking the curl of this. We are taking the cross product. Any factors within the cross product will always be completely at right angles to the resultant factors, which in our case is the magnetic field. So if the electric field points anywhere in the xy plane, the magnetic fields must be at right angles to it. The same thing goes for the fourth equation. Any change in the electric field causes new magnetic field at right angle to the electric field. Remember, we are solving Maxwell's equations. Now I want to find electric and magnetic fields formulas, so that when we substitute the left hand side, it will match the right hand side of these equations. We want the third and second equations. Remember, we can't get information about electric field without knowing the value of the magnetic field, and we can't get any information about the magnetic field if we do not know the value of the electric field. So what gives? These equations seem to be conjoined and tangled, so to speak. In math talk, we can say that it is a first order coupled differential equation. What we want to do is to decouple these equations so that they will be completely separate equations. A separate equation for E and a completely separate equation for B. Decoupling them, so to speak. Now, let us start with the fourth equation. Let us take the curl of both sides of this equation, and so we get as shown. On the left side, let us use the factor identity, so we get as shown. On the right hand side, let us exchange the order of the derivatives. Now replacing del cross E using the third Maxwell's law, we get as shown. Now combining everything, if you didn't notice, we have successfully decoupled the two equations into a second order linear partial differential equation. Just to review, the left hand side is the Laplacian operator, del square B, which is a factor 2, same as the right hand side, ignoring mu naught and epsilon naught, we have as shown. And so since both sides are factor quantities, the x component of the left hand side must match that on the right hand side. The y components must match too. Same goes for z. Just to remember, we are now finding the solutions to the second order decoupled differential equation. As we had seen, these really three separate equations. One for x, one for y, and one for z. Now we are going to try some functions on how they will solve our equations. Not that we are trying trial solutions for the x component, which is just the same for the y component, and so for the z component. Now I want to look for a function f that might obey the equation as shown, with alpha just a constant. Say partial sub t square f was just proportional to the original f, and similarly for partial x square f, we want to look for a function whose second derivative is equivalent to the original function apart from e to the x, so to say. Can you remember any? Yes, any cosine or sine function fit here. Partial t square cos t is equivalent to negative cos t. We are going to allow for f to have both an amplitude and frequency. F is equivalent to a cos omega t, where we have omega to be the angular frequency in radians per second. So if we have partial x square bx to be as shown, and if both partial x square bx and partial t square bx are proportional to bx, then we are on the right track. We know that partial x square a cos omega t is equivalent to 0. So we need to add some spatial dependence, some x, so to speak. We are going to propose an ansatz, a trial solution, so to speak. For those who took differential equations classes, I know this word, ansatz, went on top of our heads. It's just an example solution, a trial solution. The product of a function that depends only on space times a different function that depends only on time. Looks like the good old chain rule is in our favor. If partial x square fx is proportional to fx and partial t square gt is proportional to gt, that is, they are sine and cosines, then we have partial x square bx as shown. Also, partial t square bx as shown. And so we see that partial x square bx is proportional to partial t square bx, which is exactly what we need. Now let us consider these two functions, our separable solutions. F is the frequency that is waves per seconds. K is the number of waves per meter. You can think of Kx as the spatial frequency analogous to Ft, which is the time frequency. Now calculating the derivatives of our two functions. we have partial x square fx and partial t square gt as shown. And so if our magnetic field is expressed as bxxt as shown, provided by our answers, then we have partial x square bx and partial t square bx as shown. But let's just check. Our guess bxxt is as shown with partial x square bx to be as shown. So it's okay. And so now we need to ask ourselves, does this obey the second order linear partial differential equation resulting from Maxwell's equations? Is partial x square bx as shown? Now replacing partial x square bx and partial t square bx with expressions as shown, but the left must match the right. So cancelling terms, we get as shown. And so the question we need to ask, does our ratio match the actual numbers of mu naught epsilon naught and the units? Then those are the exact functions that are gonna solve Maxwell's equations. Now let us just look at the units of the ratio f on k as shown. This means that our f on k represents a velocity. Isn't it incredible? And so letting f on k be equivalent to v, then our equation will be satisfied when f on k square is equivalent to v square, which is equivalent to 1 on mu naught epsilon naught. Then what is the exact value of v? We know that mu naught is the permeability of free space, a magnetic constant, and it has a defined value. And epsilon naught is a dielectric permittivity of free space, and it too has a determined value. And so we are able to find the value of v, and we find it to be 2.998 times 10 raised to 8 meters per second, which is what? Which is the speed of light. This is the solution to the Maxwell's equations. The speed of light is the solution to the Maxwell's equations. The only solutions to Maxwell's equations have the property that they propagate at the speed of light, which are combination of magnetic fields and electric fields orthogonal to one another, carrying with them energy at that specific velocity, which is the speed of light or any electromagnetic radiation specifically. It is not only light that travels at that speed, all electromagnetic radiation specifically. And so James Clerk Maxwell created light, at least mathematically. Whether this was just a coincidence or a deliberate attempt, it doesn't matter. What matters is that it is correct. This episode is brought to you by Cisco Educational Premium. The atom is the basic building block of matter around us. Your body, your clothing, your chair, your bed, even the device you're watching this video on is made of atoms. The idea of the atom is basically the reason why chemistry exists. The periodic table of elements is basically built on atoms. Ever since the idea of the existence of atoms was put forward by the philosopher Democritus, who said that the universe is made of atoms and the void in which they exist. This idea was since given a solid grounding by scientists, particularly chemists and physicists, proving its existence by scientific method. Today, there is solid evidence that atoms exist, and when we say that atoms exist, we really do know what we are talking about. An atom is most efficient as a dense and compact nucleus encircled by orbiting electrons. This concept naturally raises the question, how do
electrons sustain their motion around the nucleus without slowing down? This question became a major concern in the early 20th century and led to the development of quantum mechanics itself. During this time, physicists were making strides in understanding atoms and recognized that each atom contained a positively charged nucleus with a considerable mass surrounded by tiny negatively charged electrons. Armed with this general understanding, they sought to construct a more detailed model. Initially, scientists drew inspiration from the solar system with a dense nucleus, the sun orbited by smaller particles, the planets. However, this model posed two significant issues. First, charged particles that accelerate must emit electromagnetic radiation by observations and at least by Maxwell's equations. Since electrons are charged and accelerate during their orbits, they should emit radiation which will cause them to lose energy and quickly spiral inward into the nucleus. However, atoms are known to exist far much longer than a picosecond, making this model incorrect. Secondly, atoms were observed to emit radiation at specific frequency, unlike the continuous emission expected from an electron following the solar system model. Niels Bohr, a renowned Danish physicist, was the first to propose a solution to these problems. In 1913, he suggested that electrons in an atom do not just occupy just any orbit but confined to specific distances from the nucleus. He also proposed that there was a minimum distance an electron could reach beyond which it could not move any closer to the nucleus. Those ideas were not just mere speculations. They were built on the work of German physicist Max Planck, who had proposed the quantization of radiation emission a little over a decade. According to Planck, objects could only absorb or emit radiation in discrete chunks, not in any arbitrary value. These discrete chunks were characterized by constant value known as Planck's constant, which had units akin to angular momentum. Bohr adopted this concept and applied it to electrons orbiting a nucleus. He asserted that the smallest possible orbit of an electron will have an angular momentum equivalent to 1 Planck constant. Higher orbits would have integer multiples of the Planck's constant, such as twice or 3 times its value, but never fractions like half or 2 and 3. The full comprehension of why electrons possessed specific orbits and well-defined energy levels required the more complete development of quantum mechanics. Electrons, like other matter particles, exhibit both particle and wave behavior. While we might envision an electron as a tiny planet orbiting the nucleus, we can usually visualize it as a wave enveloping a nucleus. Waves confined within a limited space must adhere to specific rules. They cannot have arbitrary wavelengths. Instead, they must consist of standing waves that fit precisely within the space. This is analogous to playing a musical instrument. When you fix the ends of a guitar string, only specific wavelengths produce distinct notes. Similarly, the electron wave circling a nucleus must fit the available space, and the nearest orbit is determined by fast standing wave of that electron. Future advances in quantum mechanics would continue refining this model, but the fundamental point remains unchanged. An electron cannot approach the nucleus any closer due to its inherent quantum mechanical constraints, which prevent it from occupying smaller space. However, an entirely different approach to understand this situation do not rely on quantum mechanics at all. Instead, it considers the various energies involved. An electron in orbit around the nucleus experiences electrical attraction towards the nucleus, constantly being pulled closer. At the same time, possesses kinetic energy trying to propel it away from the nucleus. For a stable atom, these two forces are in equilibrium. In fact, the total energy of an electron in orbit, which combines its potential and kinetic energies, is negative. Consequently, adding energy to the atom is necessary to remove an electron. This concept parallels the behavior of planets orbiting the Sun. To remove the planet from the solar system, energy must be added to the system. One way to envision this scenario is to picture an electron falling inwards towards the nucleus due to the attractive electric charge. However, because of the principle of quantum mechanics, the electron can never reach the nucleus, becoming perpetually in a stable orbit. Nevertheless, this situation is permissible according to physics because the total energy of the system is negative, signifying its stability and binding components together to form a long-lasting atom. Everything around us is composed of atoms. All the matter in the observable universe is estimated to be more than 10 quadrillion quintillion. This number is 1 followed by 78 zeros. Atoms are tiny particles consisting of electrons, protons and neutrons, which are in turn made up of quarks. The origin of these particles that make up atoms can be traced to the Big Bang. The Big Bang theory explains the beginning of the universe, where an immense amount of energy condensed, leading to the formation of atoms. There are more technical details than this, which we are going to look at them. To understand the scientific perspective of the Big Bang, we need to examine the events of the early universe. Unfortunately, we do not have a definitive understanding of precisely when the universe started, or if it indeed started at all. Our base model, the standard model of cosmology, allows us to trace back time close to the beginning, but we encounter a barrier at t is equal to 1. This theory predicts a singularity, a moment of infinite density where all matter and energy were compressed into an infinitely small point. Most physicists predict that this prediction may not be entirely accurate. We can only go back to 1 Planck time, which is about 10 raised to negative 43 seconds. Before this, we have no knowledge of what occurred both by observation and mathematics. So while we get very close to the beginning, it is not precisely at t is equal to 1. Understanding the events of this incredibly small time scale requires a quantum theory of gravity, where gravity, which explains the behavior of large objects, meets quantum mechanics, which governs the behavior of particles at tiny scales.
Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So how do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.